Welcome to this lesson. Imagine a diode as a one-way gate for electric current. But this gate does not open or close mechanically. It opens and closes because of what happens inside the P-N junction. Let us understand this step by step, because this is the foundation for diode rectifiers. We begin with the unbiased diode, where no external voltage is applied. So, the diode voltage, Vd, is 0 volts. We see that even without an external supply, a depletion region already exists at the junction. This happens because holes from the p-type region and electrons from the n-type region diffuse across the junction. When they recombine near the junction, they leave behind fixed ions. On the p side, fixed negative ions are left behind. On the n side, fixed positive ions are left behind. This central region has very few mobile charge carriers, and hence it is called the depletion region. It acts like a voltage barrier that opposes further diffusion of majority carriers. Now look at the diode symbol and polarity. Since there is no applied voltage, the diode is neither forward biased nor reverse biased. So, Vd is 0 volts. Next, observe the carrier flow diagram. Minority carriers can move across the junction in one direction, while a small number of majority carriers may also cross due to thermal energy in the opposite direction. Under no bias condition, these two flows are equal and opposite. Therefore, the net current is 0. The key point is that an unbiased diode already has a depletion region, but the net current through the diode is 0. Now let us move to the reverse biased diode. In reverse bias, the positive terminal of the external supply is connected to the n-type side, and the negative terminal is connected to the p-type side. Therefore, the diode voltage Vd is negative. Observe the internal charge distribution. The external voltage pulls holes in the p region away from the junction and pulls electrons in the n region away from the junction. Because of this, the depletion region becomes wider. A wider depletion region means a larger potential or voltage barrier. This larger barrier strongly prevents majority carriers from crossing the junction. So, majority carrier flow is almost completely blocked. Now look at the diode symbol and current direction. In reverse bias, the conventional current is opposite to the normal diode arrow direction. This current is denoted as Is, the reverse saturation current. In the carrier flow diagram, majority carrier flow is shown as approximately 0. However, minority carriers can still cross the junction. These minority carriers are thermally generated, and they produce a very small current. This current is called reverse saturation current. It is usually in the nanoampere to microampere range and remains almost constant even when reverse voltage increases, as long as the diode is not taken into breakdown region of operation. The key point is that in reverse bias, the depletion region widens, the voltage barrier increases, majority carrier flow is blocked, and only a very small reverse saturation current flows. Now let us move to the forward bias diode. In forward bias, the positive terminal of the external supply is connected to the p-type side, and the negative terminal is connected to the n-type side. Therefore, the diode voltage Vd is positive. Observe the internal charge distribution. The external supply pushes holes in the p region toward the junction and pushes electrons in the n region toward the junction. As a result, the depletion region becomes narrower. A narrow depletion region means a smaller barrier. Once the applied voltage is large enough to overcome this barrier, majority carriers cross the junction easily. For a silicon diode, this usually happens around 0.6 to 0.7 volts. Now look at the diode symbol. In forward bias, the conventional current ID flows in the direction of the diode arrow, from P side to N side. This is the normal conducting condition of a diode, also called the on condition. In the carrier flow diagram, minority carrier flow is still present, but it is very small. The important part is the large majority carrier flow. Holes move from the P side toward the N side, and electrons move from the N side toward the P side. The result is a large forward current. Also remember that in forward bias, the diode current increases exponentially with the applied diode voltage after the knee voltage. That is why a small increase in forward voltage can produce a large increase in diode current. The key point is that in forward bias, the depletion region narrows, the barrier reduces, and the diode allows a large current to flow. Let us now connect this idea to rectifiers. A rectifier uses the one-way current property of the diode. During the half cycle when the diode is forward biased, it conducts and allows current through the load. During the half cycle when the diode is reverse biased, it blocks current, except for a very small reverse saturation current. Finally, remember two important points. A PN junction diode conducts easily in forward bias and blocks current in reverse bias. Also, conventional current direction is opposite to electron movement direction. This understanding will help us clearly analyze half-wave, full-wave, and bridge rectifiers.